Good morning, everybody. Today we're going to start on chapter 18. We are going to start off with a concept called electrophilic aromatic substitution. Or EAS. And this is going to be a concept there's a bunch of different reactions that use kind of the same principle. We're going to be dealing with benzene rings, what we're going to have happen is our benzene ring is going to attack an electrophile. So I'm just going to draw as an E plus. This is going to break our aromaticity. And then we'll have some sort of base come in. Pull off this proton here to re-aromatize. And put a substituent on this aromatic ring. So as a review, we're going to talk about this a lot today, or use this term a lot today. There's 3 different positions on an aromatic ring. Let's take toluene, for example. So our first position, which is directly 1 carbon away. Oh my god. Yes. Is referred to as our ortho position. Two carbons away is going to be called meta. And then our furthest position away is referred to as the para position. A lot of these reactions are going to be specific for, well, they're all going to be specific for either orthopara or meta. And we'll talk about what causes them to be specific for one versus the other in a second. Let's start off by doing one reaction, though, just to kind of get into it, and then we'll kind of talk about these, what causes it to go to what position. So let's take just benzene first. We're going to add in Cl2 and AlCl3. Our Cl2 and our AlCl3 are going to form a complex that looks something like this here. Our benzene ring is going to do an attack. In order to chlorinate the ring, AlCl4, which is what we just made, is a Lewis base. So we can pick up this last proton to give us a chlorination product. Depending on what type of substituents we have on our ring, this can change the kind of product we get. So let's start with just, I'll put it on a new page. We have something like phenol. In Cl2, AlCl3. This is going to dictate what position our Cl2 adds to. So taking a look at phenol itself, it has a couple of different resonance structures we can look at. So it's what is referred to as electron donating. And really what that just means is that it's pushing electrons into the ring. So when we do its resonance structures, the electrons are going towards the benzene ring. We're ending up with a negative charge in the ring. So the first resonance structure we're going to get is going to put a negative charge on an ortho position. Our next one puts it para. And our last one puts it back to ortho. So because of this, our aromatic ring is building up charge on these ortho and para positions. So when we add in our complex, we are most likely to have it attack from one of these two positions. So this can either generate a chlorine on the para position, or one of the ortho position. From here again, we'll have our AlCl4, pull off a proton, re-aromatize. And this reaction will give us two products. So this OH here is what's referred to as an ortho-para director. As it gives us both the ortho and the para products. We'll talk a little bit more about like which one might be major later on. For this one, you might get a little bit more ortho, because there's technically two ortho positions. Then there's a bit of a steric issue because the OH is larger and the para position is completely open versus being blocked a little bit by like the electron cloud here. So for the most part, you tend to get kind of almost like a 50-50 mixture. All right, so that's an ortho-para director. A meta director is going to be what's referred to as an electron withdrawing group. They're a little easier to recognize because they really just have any sort of carbonyl for the most part. So taking a look at almost the exact same reaction. With benzaldehyde, Cl2, AlCl3. This is referred to as a electron withdrawing group. And that just means that we're going to be pulling electrons out of the ring. So before we were building up a negative charge in the ring, now we're going to be building up a positive charge. So our first resonance structure should look something like this here. And we can move this around the ring. Because we're building up a positive charge, at our ortho-para positions, that makes them dramatically less likely to attack. And it's going to make this favor having the electrons come from these meta positions. So it's not that we're building up a negative charge on the meta position like we were building up a negative charge in the ortho-para before. It's simply that the ortho and para are just worse nucleophiles now. So we're going to be forced to use our meta position in order to do these attacks. When we have this meta director here. So now we'll have the same thing happen. AlCl3, or I guess AlCl5. So Cl, this complex will generate we're going to have our ring attack at the meta position now because it doesn't have a positive charge built up on it. We can pull up this proton, and we're going to generate a meta product. So this benzaldehyde here is going to be what's referred to as a meta director. And we're going to have two groups. We're either going to have orthopara directors and we're going to have meta directors. Technically, we're going to have 6 groups that are kind of ranking them as how good they are of orthopara versus meta directors. But there's really just 2 main groups, which is going to be, is it an orthopara or is it a meta director? So let's take a look at the groups. I'm going to go vertical for this one. So our group 1 is going to be our strongly activating groups. That's going to be things like phenol. We just saw that this really makes a nice negative charge. As well as aniline. We also have methyl groups here instead of NH2s. These are considered our strong. This is our group 1. A little bit better. And these are orthopara directors. It falls into our orthopara director categories. Okay, next we have group 2, which is going to be our moderates. And this is going to be things like an ether, an ester, and an amide. The reason that these are kind of moderates, especially looking at the ester and the amide, is that we do have this resonance into the ring. But we also have this resonance over to this side. So we're kind of splitting our resonance between those 2 directions. And it makes it, instead of like donating 100% into the ring, it's donating 50% into the carbonyl, 50% into the ring. So it's not as good of an activator, but it is still in this pretty medium or moderate one. Our weak activators are group 3. Is going to be things like carbon, get a little bit of what's referred to as hyperconjugation. It donates a very small amount into our ring. It's enough to still force it to the ortho-pair position. This is going to move us into our deactivators. Our group 4 here, which is our weak deactivators, are going to be things like halogens. And this is going to end our ortho-pair directors. Group 5 and Group 6 are going to be meta directors. They're going to start donating enough negative charge into the ring that it's going to make it favor the other direction. So our Group 5 is really going to consist of pretty much anything that has a double bond or carbonyl next to our ring. So that'd be things like a ketone, aldehyde, carboxylic acid, ester. Is good. Also noting that this ester here is different than the one up here. We're connecting the carbonyl to the ring as opposed to the oxygen. What else we got? Amide. Again, different amide. We're connecting the carbonyl and not the nitrogen. Nitrile. So C triple bond N. Or a sulfate. Our final group is going to be our group 6, which are really our strong activators or deactivators. It's going to be things like nitro groups, so I'm going to draw it twice just so you guys see. It looks like we're going to use these a lot. So you'll see this drawn both ways. Amines with 4 substituents on them. So amine with a positive charge here. I'm going to run over into this other section just because I'm going to run out of room. Can't control the ring. And this is going to be carbon with 4 halogens on it. It has enough induction to cause this. So again, X is equal to the same as it was up here. Chlorine, bromine, or iodine. Okay, so using this table, we're going to kind of assess everything from now on. I'm going to take a photo of it so we can pull it back up. when we have a reaction, let me, that doesn't give me an easy way to just drop it in there. Okay. Not bookmark. Report back. Well, for instance, when I have toluene here and we add in Cl2, AlCl3, we're going to be able to go and look at our table that we made and say that this is a group 3. It should be an orthopara director. So we know that our product is going to add our Cl2 to these positions. Versus if we had this ester here, we would say this is a group 5. It's a meta director. So when we generate a product, it should add to our meta position. If we have a combination, like so, we would assess this, we'd look at it, we'd say, and basically your lowest group is going to trump. So we have an OH here, this is group 1. We have a CH3 here, this is a group 3. So 1's going to trump 3, bigger or smaller number is going to be better. This is going to be our higher priority group. So we're going to add orthopara to this group 1 here. Still doing a reaction Cl2, AlCl3. So our orthopara positions relative to that OH would be here. This one is blocked by the CH3, so we don't have to worry about it. And here, so we get 2 products from this reaction. Like so. All right, we are going to talk through a whole bunch of reactions that use all of these principles. We'll do a couple of them, take a break, and then go back and do some more. So we did chlorination. We can also brominate. Brominations will be very similar to chlorination. I'm going to use phenol as our example here. It comes from group 1. It's an ortho-para-director. So I'm just going to abbreviate it as OP director. In order to do this reaction, we're going to add in Br2 and FeBr3. It's going to form almost an identical complex to what AlCl3 formed. We just have a different metal and bromines now. I'm going to draw out the mechanism for generating the ortho or the, let's do the para product. You could also do the ortho one. So we're going to come in and attack this bromine. Break our aromaticity. We made another Lewis base, which is FeBr4. Grab this proton, re-aromatize, and this lets us generate our para products. Because we're dealing with an ortho-para director, we could also have the ortho product.
That's two major product.
Yep, 2 major products.
Thanks.
Yeah, and same thing with the Cl2. You would get 2 major products from that. All right, so let's talk through one more of these, and then we'll take a little bit of a break. So we're going to talk through how to do sulfonate. So we're going to be adding in what's referred to as fuming H2SO4. I'm going to take a meta director this time. So benzaldehyde here. This comes from group 5, which makes it a meta director. Which just means that's where our product is going to form. If we take what's referred to as fuming H2SO4, it's really just boiling H2SO4. What will have happen is 2 H2SO4 molecules are going to interact with each other. We'll eventually have one steal the proton from the other one. Make a water. This can get kicked out. in order to make our electrophile. From here, we're doing our normal reactions. So our meta position on this benzaldehyde is to come in, do an attack. In order to kick up this sulfate carbonyl, well, not carbonyl, sulfonyl. In our very first step up here, we generated HSO4 minus. So we can grab this proton with that base we made. It'll cause us to re-aromatize and give us our product. Can also be drawn as SO3 for SO3H here. So these are the same thing, just different ways of drawing them. Either as drawn out physically or just abbreviated as SO3H. All right, so just as a bit of a review, we're going to just talk through these reactions one more time. I'm going to go back to diagonal or horizontal. If we have an ortho-para director, like this amide here, throwing in AlCl2, Cl2 and AlCl2. AlCl3 here. Because we have an ortho-para director, this is a group 2. We're going to get 2 different products. If we were to have the opposite group, oh, sorry, no, I did this backwards. This is the group 2. This is the group 5. Okay. Our group 5 is a meta director. Oh, I'll do the product trunk too then. Okay. Our meta director is going to push our chlorine to the meta position. Similarly, I'm not going to draw each of these, but BR2 So taking our orthopara director, throwing in BR2, FeBr3. Lets us brominate. Orthopara, and then feeding H2SO4, we'll use our group 5 for this one. Again, this is a meta director. So it's going to push our SO3H to this meta position. So these are the 3 reactions we've learned so far: chlorination, bromination, and sulfonation. Let's take about a 7-minute break, and when we get back, we will talk through a bunch more of these reactions. They all kind of follow similar patterns. So let's meet back here at 10:06. Just kidding. All right, so let's move on to nitrosylation. It is a group 3, which makes it a orthopara-director. We are going to add in nitric acid, which is HNO3, along with H2SO4. What's going to happen is these two acids are going to interact. Nitric acid is a stronger acid than sulfuric acid is a stronger acid than nitric acid, so the proton is going to end up on the nitric acid. You're going to kick out the water here. I'm going to have us just lose a proton from this step. And we are going to make this nitrogen electrophile here. So this electrophile can get attacked by our toluene up top. It's an orthopara-director. I'm going to draw the mechanism for the ortho position. I messed around with my... Oh, I did it right. Never mind. And now we can have this HSO4 made on the top. Come in, pick off our last proton. To generate a nitro group. You could also have it, because we're dealing with an orthopara-director, could add to our para position. The other way we can draw these if you draw this fully out, it'll look something like this. All right. We're going to move on to some ones that make carbon-carbon bonds. Actually, that's not true. We're going to do one reaction first. So nitro groups can be reduced to make amines. We don't have a direct way of making an amine. Let's say we do this with a meta-director, though. Or actually, just take the same thing. So throwing in HNO3, H2SO4. If we were to then to take one of these and add it in iron, HCl, NaOH, we'll be able to reduce these. Down to amines. And eventually when we get to synthesis, this will be important. Right now, at this top phase, you'd have a group three and a group five in solution. So if you're doing a reaction, you can see how group three would be the one that trumps it. If you try to chlorinate from this position, you get a different product. Versus if you try to chlorinate after we reduce it, now we have a group three and a group one. So we would flip our priority from favoring the group three to the group one, and that'll change which products we generate. So we might get to that today. It might have to be a Monday thing. We'll kind of see how long it takes us to get through the rest of these reactions. Although we only really have a couple left. So let's take a look at what's referred to as Friedel-Crafts alkylation. So Friedel-Crafts alkylation is where we're going to take let's say this brominated bromobenzene here. Adding in this haloalkane and AlCO3. We're going to form a complex initially pretty similar to what we were forming before. But this is going to fall apart and just end up generating a carbocation. So from here are bromine is a group 4, which is still an orthopara director. I'm going to draw the para mechanism. It can do an attack on this positive charge. From this point, we've generated our Lewis base, AlCl4, pull off a proton, re-aromatize to give us our final product. And these alkylations in particular start to get into this steric concept where we're going to end up starting to form a major product on this para position. Versus the ortho position, mostly due to the fact that this is a very large group we're adding. And we're starting to get this interaction here where these two are going to repel each other. It's going to be a lot easier to add it because of how large the group is. Adding it here is going to be a lot easier than adding it to this position. So that makes this start to form a major, specifically on our para position. Wasn't the case so much before because we're just adding things like BRs and CLs. They're much smaller. Okay, because in this step here, we make a carbocation, we have to think about rearrangements. So if we were to take this chlorobenzene here, in AlCl3, we're going to form a complex. That looks something like this. This can fall apart. To give us our carbocation here. From this point, we can have a hydride shift. And now when we do our chlorination, or sorry, our EAS reaction, we're going to end up alkylating and forming a different product than we normally expect. AlCl4. Can help us re-aromatize. And this is going to give us our rearranged product. So to get around this, we are going to do what's referred to as Friedel-Crafts acylation, and then we're going to be able to reduce it. So this gave us a rearranged product. If we want to avoid that, we could instead add in the acylated form in AlCl3. So we're yet again going to form a complex that looks very similar. our complex is going to fall apart. But now we have this oxygen to stabilize our positive charge, so it doesn't need to do any sort of rearrangement. We can do an attack in this position, generate our product, which is loss of aromaticity. Pull off this proton. To get our product. Again, these are pretty large, so they're going to favor this pair position over the meta one. If you have an ortho director, it's going to add ortho either way. Okay, so this didn't exactly get us what we wanted. If we take a look at our previous reaction, I should give you guys a second to keep writing this. We took bromobenzene, we added in this alkyl halide. It rearranged us. We threw in the acyl version of it instead. That gives us similar to what we want, but it's not quite what we want. So the last thing we have to do is throw in a reducing agent. So adding in zinc HCl, or sorry, zinc mercury HCl. Lets us reduce this down to what we originally wanted. So now we're adding what looks like this group here. We just had to do it through a two-step process where we added the acyl group and then reduced the acyl down to our actual product here. All right, let's do a little bit of some minor syntheses, and then we'll do some more extreme ones on Monday. So find some. All right, let's talk through making this compound here. So there's two different groups we're adding. One of them is an alkyl group. The other one is this nitro group here. So that's two different reactions we can do. If we did, let's add the nitro group first. We are going to run into a problem. And the problem is that this is a group 5. It's in the meta director. So it would add to one of these two positions. Looking at our final compound, that is not where our alkyl group is. So if we try to do our alkylation here, we're going to get the wrong product. That's where we kind of get into this concept of like where your order is going to be really important. So instead, if we do our alkylation first, we now have a group 3, which is an ortho-para director. It's pretty large, so our ortho group is going to be pretty blocked. We take a look at these ortho positions relative to this isopropyl group that's on here. These are fairly large. It's going to be a lot easier to get to our para position. So at this point, when we add in HNO3, H2SO4, this can easily shove our reaction towards the actual product. So order of operations is really important for these. Doing them out of order can cause us to get incorrect products. I'm going to give you guys a couple of these, have you work through them. And then we'll talk them together and probably be done for the day. Let's see, where are they? All right, I'm gonna give you guys, let's say 5 minutes to do the first one. So we'll meet. Let's say 4. We'll meet back here at 10:38. Talk the first one, and then I'll give you guys a little bit more time. We'll talk at the second one. If you get through the first one, feel free to hop in on the second one. All right, let's take a look at this first one. We've got 2 different groups on here. We have a chlorine and we have an amine here. Taking a look at them, they're both ortho-para directors, which can be complicated because they are meta to each other. So we're going to have to take a look at how they're made and kind of figure out what the best way to go is from here. So in order to make an amine, we would have to go through a nitro group. If we added the chlorine first, it's an orthopara director. That's going to be problematic because we want these to be meta to each other. So by adding this nitro first, we now have the correct director. This is a meta director. This has the ability to add Cl2 to it. So we should do that before we do something to change it and make it not have that option. If we were to reduce it first, for instance, we get back to a orthopara director. So it's good to take care or to take advantage of the fact that we have a meta director while we have it. So it's a meta director. It's going to give us a product in our correct position for the chlorine. And then from here, if we throw in our zinc, mercury, HCl, this is going to let us reduce this down to our final product. Okay, I'm going to give you guys till 10:45 to try to do this next one. Yet again, it'll be an order of operations one. So do your best, and we will check back in 4 minutes. Okay, so taking a look at this, we have 3 different groups on here. That's the wrong thing. We've got a group 5. It's an ortho or meta director. We have this nitro here. It's a group 6, also meta director. And we have an alkyl group. It's a group 3. Makes it an ortho para director. If we add the group 5 first, we would then be able to add the group 6. Those are both meta directors, which means if we tried to add something else, it would go to this position. Same thing if we added the group 6 first, followed by the group 5. So that's going to imply that we have to add this group 3 one first in order to actually get something in the positions that we want them to be. Because the ortho and the para positions relative to our group 3 is where our group 5 and 6 end up. So with that in mind, how do we add this alkyl group first? If we were to try to add it like normal, it would rearrange. So we're gonna have to go through an acyl intermediate. Doing an acylation. Gets us this meta director, which is not what we want. So we have to reduce it first with iron, HCl, NaOH. And this puts us into a position to do what we actually want. So now we have a group 3, it's an ortho para director. Our ortho is somewhat blocked, so if we were to add an acyl group, it should add para. From here, we have a group 5 and a group 3. Our group 3 is going to trump our group 5. So we're still adding ortho para to this group 3. Our para is blocked, which means all we have open is these ortho positions. So from here, adding in NO3, H2SO4 allows us to get to our final product. Any questions on this one? If not, we're gonna.
Can we, excuse me, can we add the first one with AlCH3 with the group carbonyl with Cl first? Can make the group 3 first? Can we do that?
Like if you added in
Yeah.
this. The problem is that this, when it forms a carbocation, is going to rearrange. So this would actually give you a rearranged product. A little rough. Which is why you have to go through the acyl first.
Okay, got it. Thank you.
You're welcome. Okay, I'm going to stop here for today. We will pick this back up on Monday. So I will see you guys then. Or in recitation if you have it later today.